Okay, so now we need to talk about writing Lewis structures with the octet rule. So here we see two different separate Lewis structures and how they're coming together to form a covalent bond here, hydrogen and bromine. Bromine has 7 valence electrons, hydrogen has 1, and they're both able to share an electron. So bromine would have 8 valence electrons, or full shell, and hydrogen would have 2. And so here you can see how with sulfur has 6 valence electrons, and so the element needs 2 more electrons, and so it's going to form single covalent bonds with 2 different hydrogen atoms. Okay, so it can also have 8 electrons around the atom, and then each hydrogen atom, it has 1 electron and 1 shared electron, so 2 total around it as well. So each element is happy and in what it needs. So here we have 2 nitrogen atoms. They each have 5 valence electrons. So you can't get to a point where they're each are going to have 8 because with a single bond, because basically it needs to be able to have 8 around it, and it needs 3 more. And so basically you're going to end up having having to share 3 electrons with another nitrogen atom, and you basically end up with a triple bond in between the 2 nitrogen atoms. And so you have 2, 4, 6, 8 here around nitrogen, and 2, 4, 6, 8 around the other nitrogen atom, and you're able to have a complete octet around both nitrogen atoms. So this is something we didn't talk about earlier, and that is the stepwise process of how to draw out your Lewis structures. And so it's a step-by-step procedure that you may want to write down and follow as you're learning how to draw out Lewis structures. And then eventually you can ditch the list and just do it automatically. Sometimes you have to play around with the structure a little bit to figure out what's the best orientation in order to get an octet around each element. But when you're starting, it's always good to have sort of a check-off list when you're doing this sort of thing. So the first thing you're going to want to do is determine the total number of valence electrons. Okay, if it's a cation, you're going to have to subtract 1 electron for each positive charge. So if it has a +2 charge, it has 2 fewer electrons than it normally would as a neutral atom. For anions, add 1 electron for each negative charge. Then you're going to draw out the skeleton structure of the molecule or ion, arranging the atoms around the central atom. So generally, the central atom is the least electronegative element. Okay, and so a lot of times that's going to be carbon, or it's going to be a non-halogen. But depending on the other elements too, sometimes it could be a halogen, just depending. But generally it's not, because halogens, like fluorine for example, is the most electronegative element. It's not going to be in the center of the molecule. So just keep that in mind. You connect each atom to the central atom with a single bond, okay, an electron pair, and distribute the remaining electrons as lone pairs on the terminal atoms, except for hydrogen, of course, because once it has a single covalent bond, hydrogen has its s subshell filled. Okay. And completing an octet around each atom after that. And so your terminal atoms, of course, have to have an octet. You're going to want to put lone pairs on your terminal atoms first, and then if you have any extra, then they would go on the central atom. And then rearrange the electrons on the outer atoms to make multiple bonds with central atoms in order to obtain octets wherever possible. So generally you start with single bonds, and if you need more electrons to make an octet possible for an atom, then you end up taking away lone pairs to create double or triple bonds between atoms. So we're going to go ahead and look at a couple of examples here. We're just going to scroll through this quickly, and then we're going to end up doing some ourselves. So here we have SiH4, so Si silicon, it has 4 valence electrons. Hydrogen has 1 each, and there's 4 atoms. So when you add up how many valence electrons you should have 4 from silicon, 1 from each hydrogen atom. There's 4 of those, so 4 plus 4 is 8. So it should have 8 valence electrons. This is a way you can sort of check your structure after you draw it. Okay, and so scrolling down to our structure here for silicon, we see that it has 4 covalent bonds. It's the central atom. The hydrogen atoms are the terminal atoms. That each hydrogen atom makes a single bond with silicon. Okay, so silicon now has 8 electrons around it, and then hydrogen has 2 each. So here you have the structure drawn for that compound. Now here we have CHO2 minus. So carbon has 4 valence electrons. It's in group 14. Hydrogen has 1, and then oxygen has 6, and there's 2 of them, so that's 12. And then the negative charge there, you're going to add 1 additional electron because it's negatively charged. Okay. Now again, that electron is not assigned to any particular element. Okay, you use it where you need it. Okay, so you have 8 valence electrons there for CHO2. I believe we drew this out last time. So here we have carbon, we have 2 oxygens, and we have 1 hydrogen atom. And so here, this is actually not the completed, not showing the dots here. This is basically your skeleton. Okay, so carbon has 1, 2, 3, 4. It only has 3 here. There should be 4 though, so we're going to have to do something. And what we end up doing here is we have to have another double bond there. So when we add our lone pairs here, so for oxygen it should have 6, okay, valence electrons. Okay, so each of these guys have 6, and then carbon has 4. 1, 2, 3, 4. And there's an extra electron for the negative charge there, and then hydrogen has its own there. Okay, so with this structure, you see how carbon only has 4 single bonds, and we said carbon should always, or it has 3 and it should have 4. So what you end up doing is taking a lone pair from the oxygen, and this happens a lot with oxygen. It usually loses a lone pair in order to form a double bond to help out an element that's like a central element, and that's an example here that carbon needs 4 covalent bonds around it, or 8 for to complete its octet, and so oxygen is going to have to give a lone pair up in order for that to happen. Okay. Also, whenever you have a negatively charged molecule, you're going to have it in brackets with a negative sign on the outside. And that just indicates that this structure is not neutral, that it has an overall negative charge. If you think about it, when you have ions, that's the case. You're always having to indicate the charge on the ion, and that's what you're having to do here. Okay. So let me just do one more of these, and then we'll go to example 7.4 where I'll actually draw out some more Lewis dot structures. All right, let's do NO+. So the first thing you have to do again is to figure out how many valence electrons you have, and then at the end you can double check. So nitrogen should have 5, oxygen should have 6. It's positive, so that means it has 1 less electron. Okay, so instead of having 11 electrons, it only has 10. And if you notice, most of the time your total number of electrons should be an even number. You usually don't have, if you have lone pairs, they usually are pairs. They don't exist as single electrons. And you usually don't want to have a single electron if you can help it. So just keep that in mind. So here we have the structure. We have nitrogen and oxygen. So here's the sort of the skeleton structure here in brackets with the positive charge. Okay. And then the next step is to go ahead and put in your dots there. So nitrogen should have 5 valence electrons, 1, 2, 3, 4, and then 5 there. And oxygen has 6, 1, 2, 3, 4, 5. It should have 6, but we're minus 1, so we won't add this 1 electron here because it's positively charged. Now, if we look at how many valence electrons we have around each element, here we have 2, 4, 6 around nitrogen, and in oxygen we also have 2, 4, 6. So we need to have some other pair of electrons so that they each have 8 around them. And so, of course, the obvious thing to do is to take a lone pair of electrons and make a double bond between nitrogen and oxygen. And so that's what we do. And so here we can see that oxygen, we take a lone pair off of it and make a double bond. So now we have 2, 4, 6 around oxygen, and we have 2, 4, 6, 8 around nitrogen. Well, that's not going to work either because we need to have 8 electrons around oxygen. So again, we have to take another lone pair from nitrogen this time and make a triple bond. Okay, when we do that, we can see that we have 2, 4, 6, 8 electrons around nitrogen and 8 electrons around oxygen. Okay, and so finally we have a structure here that obeys the octet rule for both elements. All right, so the next thing I want to do is look at example 7.4. Where we're drawing different structures, different Lewis structures for different compounds. And so the first compound we're going to look at is HCN. Okay, so here I have HCN. And so the first step is to figure out how many valence electrons I need. And so here for hydrogen, it has 1 valence electron. For carbon, it has 4. And for nitrogen, it has 5. And so adding everything together, that makes 10 valence electrons. All right, so how do I situate this? So my least electronegative element is carbon. Okay, carbon is to the left of nitrogen, and so here carbon's going to be my central atom. Okay, so I'm going to make my little skeleton here. So I have hydrogen as a terminal atom, which is usually the case. Actually, it's always the case. And carbon's in the center, and then I have nitrogen. All right, so now I need to assign electrons here, and then see how many bonds I really need. Obviously, we're going to have to sort of count. So for each element, what I end up doing is counting. Nitrogen needs 5, so it has 1 here. So 1, 2, 3, 4, 5. Okay, and then carbon has 4. 1, 2, 3, 4. Okay, and then hydrogen has 1. All right, so hydrogen's happy because it has 2 overall here, right? Carbon, okay, he wouldn't actually draw this, but I'm just showing you all the dots here. It's one single line. Carbon here has 2, 4, 6. It doesn't have enough electrons around it. Okay, so what's going to happen here, and also nitrogen also has 2, 4, 6. So we're going to have to take a lone pair off something. And so I would take it off here, okay, and then put another covalent bond. So now it has 2. So now I have 2, 4, 6 around nitrogen and 2, 4, 6, 8 around carbon. So what I'm going to end up having to do, because nitrogen only has 6, it needs another bond here. And so I'll end up with, let me just rewrite this so it's not so sloppy. This lone pair is going to make a 3rd covalent bond. So then you're going to have 3 covalent bonds between carbon and nitrogen. And then you leave the lone pair there that was there originally. So now you have 2, 4, 6, 8 around nitrogen, you have 2, 4, 6, 8 around carbon, and then you have 2 around hydrogen. Okay, so that would be your structure for HCN. Now to go back and double check, because we added up all our valence electrons, we can just add everything up and to make sure that we have 10 valence electrons. So here we have 2, 4, 6, 8, 10. And so we're good with that. So that should be our structure for HCN. Every element obeys the octet rule. And of course, hydrogen, it needs to, so it obeys its own special rule. Okay. All right, the next formula here, C2H6. All right, so here we have hydrogen atoms that are going to be terminal atoms. Carbon is usually sort of a carbon backbone, and so it's going to be a central atom. And carbon atoms also bond with themselves, okay, to make a chain. And then what ends up happening is you have these hydrogen atoms around it. So here I need 6 hydrogen atoms around it. So I'm going to make my structural formula. We said with our structural formula, we need to attach each atom, okay, with a single covalent bond that looks something like that. Okay, so now I'm jumping ahead myself. I need to count my electrons, right? I didn't do that. So each carbon atom has 4 valence electrons, right? And so so 4 plus 4, that's 8. And then hydrogen each has 1, so that's 6. And so that's 8 and 6. So that should be 14 electrons total. All right, so let's see if that's the case. We see every carbon atom here, 1, 2, 3, 4. There's its 4 electrons there. 1, 2, 3, 4. And then hydrogen, 1, 2, 3. 1, 2, 1, 1, 1, 1, 1, 1, right? So there's 6 total there, all for hydrogen. But so carbon has 8 electrons around it, 2, 4, 6, 8. So that satisfies the octet rule. This other carbon atom also has 8, 2, 4, 6, 8. Okay, and hydrogen has 2, 2 electrons. So this structure is good to go. Now we can double check our electron number, 14, 2, 4, 6, 8, 10, 12, 14. So we're good to go with the electron number, and so we should be able to move on to the next structure. Okay, so the next structure is C2H2. All right, so what I'm going to do is I'm going to figure out number of electrons again. So here carbon has 4 electrons, and there's 2 of them. And then hydrogen, there's 2 hydrogen atoms, each is 1. So 8 plus 2, so that should be 10 electrons. All right, so again, I'm going to draw out my carbon backbone here. Whether you put the hydrogen atoms up here, down there, up and down, doesn't really matter at this point. Okay, when you take organic chemistry, it will matter. But just count your blessings, it doesn't matter right now. But so let's see, let's figure out the electrons here. So hydrogen has 1. This carbon atom should have 4. 1, 2, we'll just put here 3, 4, and then 1, 2 for this atom, 3, 4, and then dots everywhere on this paper, which I don't want to confuse. All right, I'm going to make them big so it's obvious. All right, so 4, 4, okay, and then here's an electron for hydrogen, there's an electron for hydrogen. All right, so obviously we have 2, 4, 6 around this carbon, and then 2, 4, 6 around this carbon. So that's no good. We need 8 around both of them. So what we need to do, we'll take one lone pair and put it between them. Okay, so now this guy has 2, 4, 6, and this one has 2, 4, 6, 8. Well, that's no good either. So I'm going to take this other lone pair and make another covalent bond. Okay, so let me rewrite this because it's getting messy here. So now I have 3 covalent bonds in between the carbon atoms. I've taken away their lone pairs, which you hardly ever, honestly, hardly ever see lone pairs on carbon, just FYI. So here around each carbon atom now we have 2, 4, 6, 8. Around this one, we have 2, 4, 6, 8 electrons. Around that other carbon, we have 2 for each hydrogen atom, and it's happy. So now I need to just verify that I have 10 valence electrons that I used. 2, 4, 6, 8, 10. So we're good with that. So this structure is what it should look like here with a carbon-carbon triple bond in the center. Switch this paper around. Okay. The next structure is ammonia. Okay. So ammonia, here it has, nitrogen has 5 valence electrons, and hydrogen has 1 each, and there's 3 of them. Add that together, you should have 8 valence electrons. All right, so I have 3 hydrogens. They're probably going to be around nitrogen, right? Nitrogen's going to be the center. It's the central atom there. Hydrogens can't be central atoms, right? Because you only have 1 covalent bond. All right, so I went ahead and drew out my structural formula. And now I need to assign electrons for every element. So here, this hydrogen has 1, this hydrogen has 1, this hydrogen has 1. Nitrogen has 5. 1, 2, 3, 4, 5. All right, so now that I've assigned that, let's see if that's going to work out for nitrogen. 2, 4, 6, 8. Yeah, it has 8 around there, and hydrogen can only have 2. All right, so the final structure here, I'm just going to write it where it's actually prettier than what I had before. It looks something like that. That's your structure for ammonia. Now let's verify it has 8 electrons. 2, 4, 6, 8. So it does. So it's good, and it also satisfies the octet rule. All right. Let's see. We have more examples, but I want to go ahead and switch over to the textbook so we can look at some structures that don't always obey the rules. Okay, so they're the more unique structures that we're going to look at. Okay, so exceptions to the octet rule. Many Lewis structures, the elements do not have 8 valence electrons, and we're talking about, of course, the central atoms. Terminal atoms have to have 8 valence electrons, or 8 electrons around it, shared in valence. But you have some exceptions to the octet rule. And the first exception is called odd electron molecules have an odd number of valence electrons and therefore have an unpaired electron. So when I spoke earlier about having lone pairs, sometimes you don't have a lone pair, sometimes you have a single electron there. And so it's not very common, but it does happen. So be aware of that. Electron deficient molecules have a central atom that has fewer than 8 electrons. Okay, and so sometimes the central atom has less than 8 electrons, and sometimes it has more. Okay, so hypervalent molecules have a central atom that has more electrons than needed for a noble gas configuration, meaning more than 8. So what do you do with odd electron molecules? So we call molecules that contain an odd number of electron free radicals. Okay, maybe you've heard of free radicals in biology. It's very common. It's a lot of times it's associated with aging, and rapid chemical reactions occur when you have molecules that have free radicals. So nitrogen oxide is an example of an odd electron molecule. It's produced in internal combustion engines when nitrogen and oxygen react at high temperatures. So here we see a system of what to do when you have an odd number of electrons. So first you determine the total number of valence electrons. Here we have 5 from nitrogen and we have 6 from oxygen. That adds up to 11. The odd number immediately tells you that you have a free radical. So we know that not every atom can have 8 electrons in its valence shell. So you draw the skeleton like we did before, okay, with a single covalent bond in between nitrogen and oxygen. You distribute the remaining electrons as lone pairs around the terminal atoms. In this case, you don't have a central atom, but they're both considered terminal atoms. So you're going to give electrons to the more electronegative atom. Okay, so we talked about electronegativity. The halogens are more electronegative than group 5 or 15 elements, like nitrogen. So that means oxygen is going to be given its regular amount of electrons that you would normally give it. So it should have 8 around it, 2, 4, 6, 8. And then nitrogen is going to be lacking. Okay, so here it only has 2, 4, 5 around it. Okay, so you replace the remaining electrons on the central atom. Since there's no remaining electrons, the step does not apply. But you do give the remaining electrons to nitrogen. Whatever is left over after oxygen has its 8. Okay. And then you try to rearrange the electrons in order to obtain an octet if possible. Okay, so we know that an odd electron molecule cannot have an octet for every atom, but we want to get an atom as close to an octet as possible. So in this case, nitrogen only has 5 electrons around it. To move closer to an octet for nitrogen, we want one of the lone pairs from oxygen to use it and form a double bond. So we take a lone pair from oxygen, form a double bond. Now we have 2, 4, 6, 8 around oxygen and 2, 4, 6 around nitrogen. Okay. So all right, so we cannot take another lone pair from nitrogen or oxygen because then nitrogen would have 9 electrons. So we can't do that. So here we're ending up with something that's not perfect. You're lacking for nitrogen because it has an odd number of electrons. You just have to sort of accept that fact that it has 7 valence electrons and not 8. So again, when you have an odd number, that's probably going to happen. So sometimes you have electron deficient molecules where the central atom is not going to have 8 around it. These are generally, it's generally true when you have central atoms from groups 2 and 13. So beryllium has 2 valence electrons. Okay, so obviously it only has 4 around it and not 8. Boron is in group 13, so it has 3 valence electrons. So it only has 6, okay, when it makes 3 covalent bonds with 3 fluorine atoms. And so you don't have 8 around it either. So these are electron deficient molecules. Okay. And when you start to do these, you know, it's going to be pretty natural whenever you do these. If you notice, halogens hardly ever make double bonds, you know, if ever. So just kind of keep that in mind. Hypervalent molecules occur when the central atom has more than 8 valence electrons. Here we see phosphorus has 2, 4, 6, 8, 10 valence electrons. And you know, if you have a formula PCl5, you know those chlorines are going to have 6 lone pairs, or 3 lone pairs, 6 electrons that are not bounded to anything, and then you have 2 that's part of the covalent bond. And so you have 8 total around here. So you know every chlorine atom is going to do the same thing. And so you end up having, instead of having 4 covalent bonds, you have 5 around phosphorus. Same thing for sulfur here. If it's SF6 is the formula, well, sulfur is going to have 2, 4, 6, 8, 10, 12 valence electrons instead of 8. And again, that's because, you know, it's possible for the central atom to have more than 8 or less than 8 electrons around it. Doesn't happen often, but it does happen. Okay, here we have iodine. It has 7 valence electrons. All right. And you can see here that it has, when it binds to 5 fluorine atoms, it has 2, 4, 6, 8, 10, 12 electrons around it. Xenon. Xenon's a noble gas. You might be freaking out because you think that noble gases don't actually react, but they actually do. A lot of things we say in chemistry, there are always exceptions, and so there's usually a list of exceptions. So with xenon, it has 8 valence electrons. And here, when it's bound to 4 different fluorine atoms, it has 2, 4, 6, 8, 10, 12 electrons around it. And so, again, this happens with central atoms. All right, so the next thing we're going to do is do some problems where we're dealing with structures that do not obey the octet rule.